So it's a powerful production technique. And this, we've heard it mentioned several times, is the facility for Rare Isotope Beams, which is about to be constructed here at Michigan State University. And you can see it's a large facility, but it basically does this simple thing. It takes large nuclei, breaks them up into smaller ones, and that allows us to do experiments with them. This part here is the driver LINAC. That's the part that will accelerate the nuclei to high energies. There will be target facilities, and then experimental facilities. And we're sitting over here somewhere, which is going to be part of the new accelerator facility of FRIB. And I think in some ways this is maybe the first piece of FRIB that will come into operation, even though the driver will be many years before it comes along. Now, I put this picture up because in this relatively short time, I don't have time to describe the technical features of the machine. But I wanted to just say one thing about how a machine like this comes to be built. A lot of technologies are needed to build this facility, and a lot of them have been developed here. But in fact, this is a worldwide effort to both develop these accelerators and the technology for separating the isotopes and for doing the experiments. For example, the ion source back up here at the beginning of the LINAC, those are being developed at Lawrence Berkeley lab. The technology of the LINAC itself, many laboratories have worked on this. It will be superconducting in technology. Jefferson Lab is the leading laboratory for this in the world, and the LINAC will follow many of their developments. Argonne National Lab has also been involved in this, especially in the reaccelerator cavities. The techniques for separating isotopes, preparing for the experiments, have been studied a lot here, but also internationally in West Germany, in Japan, and so on. And finally, the experimenters come from all over the world: Europe, the United States, the Far East, and so on. So it's truly an international effort that gives us the ability to put such a facility together and then do experiments with it. So now we've got our machine to... Let's talk about now what the isotopes that this facility will produce. In my little primer here on isotopes, I was concentrating right down in this bottom left-hand corner. But in fact, we know that elements go all the way from protons to uranium and beyond up here, and neutrons can go all the way out here. So the elements that we see around us lie along this black line here, similar to the black line I had on my little chart at the beginning. But the isotopes that FRIB will produce are distributed on either side. And you can see it's a broad landscape. And this is the thing that's the game changer for the nuclear physicist, the fact that instead of living on this line, we'll now be studying a landscape. A one-dimensional exploration becomes a two-dimensional one in scientific language. This is a rather technical slide about the rates at which these isotopes are produced. I'm not going to discuss it at all, except one thing, and this is a comment on these experiments that we did a long time ago at Lawrence Berkeley Lab at the Bevatron, which were the early fragmentation experiments. This is that now that the rates of the secondary beams that will be coming out of this facility are actually much greater than the primary beams that we used to start the experiments 30 years ago. So for example, the rate of a nucleus like calcium-55 is a very neutron-rich nucleus, is actually greater than the rate that we had of our primary beam at Berkeley in 1979. So now I want to kind of make a point about why it is such a big deal for a nuclear physicist to go from the one-dimensional exploration along the line to this two-dimensional exploration of the nuclear chart. So I went to Google Maps, and I got a map of Michigan. Of course, Lansing is in the center here. And we can see there's geography here. We have water and land, and it has complicated shapes. But imagine if we had to deduce that geography from a slice cut through it. Okay, we'd start from the left. Our explorer would come along, moving east. You'd see land, water, land, maybe some more water, land again. With this kind of knowledge, it's extremely difficult to deduce whether you have a lake or an ocean above you, rivers, and so on. But this is really the situation that nuclear physicists have been facing for the last century.